Hello, welcome. Let's look at this adiabatic saturator problem. A plant requires 15 kilogram per second of cooling water to flow through its distillation equipment condenser. The water will leave the condenser at 318 Kelvin. It is planned to cool the water for reuse by contact with air in a countercurrent adiabatic cooling tower. The dry bulb temperature of the entering air is the dry bulb temperature of the entering air is 303 Kelvin, and its weld bulb temperature is 297 Kelvin. The weld bulb temperature approach must be the weld bulb temp approach must be 5 Kelvin. Now the air rate to be used is 1.5 times the minimum. Specialized packing will be used, for which KYA is expected to be 0.9 kilogram per meter cube second. If the liquid mass velocity is at 2.7 kilogram per meter square seconds, and the gas mass velocity is 2.0 kilogram per meter square second. Compute the dimension of the packed section and the makeup water requirement due to evaporation in the tower. The saturated air enthalpy with corresponding temperatures at 1 atmosphere for equilibrium data is as shown below. So the corresponding is the data is as shown. I'm going to draw the data now. We have temperature in Kelvin, then we have the enthalpy, saturated enthalpy in kilojoule per kilogram. So you have a temperature of 293, you have enthalpy to be 57.57. At temperature of 303, have enthalpy to be 99.75. At temperature of 313, we have enthalpy to be 166.79, and at temperature of 323, we have enthalpy to be 275.58. Then at temperature of 333, we have enthalpy to be 461.5. So those are the values given, and we are going to start solving with these given values. So let's start solving this problem. We start by saying solution. The entering air humidity and enthalpy are those of air saturated at the wet bulb temperature of 297 Kelvin. Very important. Note that it is at the wet bulb temperature. That's what we calculate with, so that we can now say that the vapor pressure of water at 297 Kelvin. If we read it out from the table, you're going to find out that the vapor pressure of water at 297 is 2.982 kilopascal. So we can now calculate the relative humidity by saying 2.982 all over 101.3 minus 2.982 times 18, which is the molar mass, all over 29, which will give us 0.019. So that the enthalpy now will be, using the formula Cp B bracket T minus To plus Y into bracket Cp A bracket T minus To plus lambda O. So this will give us 1.005 into bracket 297 minus 273. 273 is normally the reference temperature, plus 0.019, which we already got before, into bracket 1.884 heat capacity, into bracket 297 minus 273 plus 252.3. So if we do this calculation, we get the enthalpy to be 72.55 kilojoule per kilogram. So this we can also read out from the chart. If we get to the psychrometric chart, once we consider the wet bulb temperature of 297, this 297 is similar to 24 degrees Celsius. Take note. So if we check at this temperature, wet bulb temperature of 24 degrees Celsius, we are going to find out that PA will be equal to this 2.982, and YA, Y1 or Y prime will be equal to 0.019. And we are going to also find out that H prime will be equal to 72.55. So those are the things we can read out from our graph, and from there we can continue with the rest of the calculations. Now, to calculate, to get the operating line, we need to have a sketch of what is expected to happen. So we have the liquid flowing in here with the rate 15, and we have TL2 to be 318. This is at point 2. We have the gas going out here. Then down here we have TL1 is point 1, and we have the gas going in here with TG1, which is 303 Kelvin, or the air. Now at these conditions, we have that the wet bulb temperature approach, which is given, is equal to 5. So TL1 minus TW2. So at this point we can have our TW1 to be equal to 297. So this minus this will give us 5. So that we can now calculate TL1 to be equal to 5 plus, if this goes over to here, it becomes for TW2, which is 297, which will give us 302. So that from here we can now plot the equilibrium curve, considering the saturated enthalpy curve from 295 to 325. And we take this region because it covers the operating condition temperature of 318 to 297. So with that, we can plot the equilibrium curve. Also, for us to now know where the operating line starts, it's going to start from TL1 equal to 302 and H, which is equal to the wet bulb, which is H as the wet bulb. So H at the wet bulb is, from our calculation, 72.5. So that is what we are going to be using to do our calculations. Now, that's where it's going to start. And where will it end? It will end at TL2, which is equal to 318, which is also equivalent to 45 degrees Celsius, and H, which we are going to find out. But how do we do the plot? We'll plot N to O, that is making a tangent. Then after doing that plot, we trace it to H1, which will give us 210, so that we can now calculate the slope of the line O prime N, which will give us L prime CAL all over V prime, which is actually 15 times 4.187 all over VS1. So this will give us 210 minus 72.5. We are checking the slope, all over 318 minus 302, and which will finally give us 8.594. So that's what we are going to have. Then we can make VS minimum the subject, so that we have 15 times 4.187 all over 8.594, which will give us 7.31. But we know that the actual Vx equal to Vx prime, which is equal to 1.5, because it told us it's 1.5 times the minimum. The minimum is 7.3, which will now give us 10.97 kilogram dry air per seconds. So having this, we can now find the actual slope. So the actual slope is equal to H2 minus 72.5 all over 318 minus 302, which will give us 15 times 4.187 all over 10.97, which will give us 5.725. So that H2, making it the subject, will give us 72.5 plus 91.6, which will give us 164.1. So that we can now establish ON. So we can say now that ON is established with this. So having done this, we can now move down to solving that for GX, gas flow rate of 2.7, liquid rate actually, we have that the tower cross-sectional area our cross-sectional area will be equal to L prime GX, which is equal to 15 over 2.7. So this cross-sectional area is going to be equal to 5.56. And for gas rates, which is GS prime, given as in the question as 2.0, the cross-sectional area is going to be Vx prime all over GS, which will give us 10.97 all over 2.0, which will give us 5.5. So having these two values, we choose x to be equal to 5.5 to ensure that our gx is equal to 2.73, which is greater than 2.7, and that our kya is equal to 0.9. So having that in mind, we can now say that HOG, height, is equals to G prime x over kya to give us 2.0 all over 0.9, which will give us 2.22 meters. Now to calculate NO, from this now we can simply calculate our NT, number of stages, to be equals to area under the graph, which is 3.28, and Z is equal to STOG times NTOG, which is 2.22 times 3.28. That's total height, which will give us 7.28 meter as the height of the parking. So that's what we have. But as I was explaining the graphical area, I did not draw them, so I want to draw the graph now from where we got all these. So we are supposed to have a graph of this nature, where we are starting from 290, we have 295, we have 302, we have 315, we have 318, we have 325. So this is what we have. Here we have 50, we have 164.1, we have 210, we have here 300. So this side is known as the enthalpy in kilojoule per kilogram dry air, whereas this side is the liquid temperature in Kelvin. So the equilibrium line is first drawn with the data given. Then we are going to draw an imaginary operating line to just touch here. Then we'll now from here draw the real operating line to move like this. So make sure we trace all these points. So if we do that, we are going to get what we want. So I'm still going to show a real paperwork of how this line is drawn. So having done this, we can then, having done this and drawn the real slope, we can then have our table of TLK, H prime, which we are going to determine from the graph that we plotted. This is H equilibrium, this is H prime, all in the same unit. Then finally we have H equilibrium minus H prime, inverse of it. So these values we are going to pick. We're we're going to pick values from 302.0, 305.5, 308.0, 310.5, 313.0, 315.5, 318.0, and find the corresponding H equilibrium, which we are going to have as 100, 114, 129.8, 147.0, 166.8, 191.0, 216. So we'll find this, as we already calculated this, so we can still trace it out at the various temperatures from our graph. .2. Then find this one, 0.03636, 0.04545, 0.04292, 0.03846, 0.03195, 0.0241, 0.01931. So that's what we are going to use. So having gotten this table, we can now simply plot the graph of H equilibrium minus H prime, the inverse, which you already have, against H prime, starting from this 72.5, which you already calculated, and 164.2. So if we plot this, we are going to have a graph of this shape, and the area under here is what we said, NOG, which we said is 3.28, and the total height is therefore STOG times NTOG, which is 2.22 times 3.28, which will give us the total height of 7.28, or packed height. So that is how we arrived at the final answer. But before then, we can also calculate the makeup water. To estimate the makeup requirement due to evaporation, assume that the outlet air has enthalpy of 164.1, is essentially saturated. This corresponds to the exit air temperature of 312.8 Kelvin, and humidity of 0.048 dry air. The approximate rate of evaporation is therefore Vs1 equal to Vs equal to y2 minus y1, y2 prime minus y1 prime, which will give us 10.97 bracket 0.048 minus 0.019, which will give us 0.318 kilogram per sec. Now this is equal to 2.1% of the total water in circulation. So having that, we now have this water makeup to be 0.318 all over 15 times 100%, which will give us 2.1. So this 2.1, we actually got it by saying what we have here, all over 15 times 100 over 1, and that is the makeup water. Thank you. Please hit the subscribe button. Thank you. God bless you.